third statement. Let me make sure I have the right statement here. If x tilde 1 to n, y tilde 1 to n is distributed as px 1 to n times py 1 to n, where these are the same marginal distributions as the original x and y, then the probability of such a pair appearing in the typical set is less than or equal to 2 to the minus n mutual information minus 3 epsilon, and for n sufficiently large, that same probability is greater than or equal to 1 minus epsilon 2 to the minus n mutual information plus 3 epsilon. So the proof of that statement, this probability is the sum over all x and y in the typical set. So this is the probability of independently selected pairs being in the typical set. So we have the sum over all x and y in the typical set of the independent probabilities. Like so. Okay, you know what, I actually should review this. I'm using this property a lot, so let's actually review it. So, I need to be able to express these probabilities. These are in the typical set, therefore their probabilities must be very close to average, as I mentioned. So let's review what exactly that is. Remember that the typical set, if x is a component of one of the pairs in the typical set, then it must be true that minus whatever n log probability x from 1 to n minus the entropy is less than epsilon, or less than or equal to, doesn't really matter. What does that mean? I could rewrite that as minus epsilon is less than negative 1 over n log px 1 to n minus h of x is less than epsilon. Excuse me, that magnitude goes away. So basically all I did there was I got rid of the magnitude. If I add throughout by h of x, that throughout by minus n. Whoops. Because I multiplied by a negative number, these switch sides. The inequalities switch. And then finally I take 2 to the power of everything. So this is the property that I explained a second ago. It's equivalent for y and for joint between x and y. In fact, let me write that all down over here. For x, it's 2 to the minus. This basically sandwiches the probability of any sequence in the typical set, any x sequence in the typical set, somewhere around or very close to 2 to the minus nh of x. So 2 to the minus n h of x plus epsilon less than or equal to px1 to n, less than or equal to 2 to the minus n h of x minus epsilon. We can go through exactly the same derivation for y. So therefore, 2 to the minus n h of y plus epsilon less than or equal to probability y1 to n less than or equal to 2 to the minus n h of y minus epsilon. And we can also, it doesn't really change anything if we go to joint probabilities and joint entropies. So therefore it must also be true that 2 to the minus n h of x and y plus epsilon less than or equal to probability x1 to n and y1 to n less than or equal to 2 to the minus n h of x and y minus epsilon. So this is what I just proved. These two are proved in the same way, and if you're looking for an exercise, you can derive these two on your own. They're derived exactly the same way as the first one. But we need them for now, so let me rewrite what I just had a second ago. So the probability that x tilde and y tilde is in the typical set, so in other words, independently selected x and y are in the typical set, is equal to the sum over all of the pairs x and y in the typical set of the probability of all of these events occurring. The probability of all these events occurring is, because they're selected independently with the same marginals as x and y, it's just the marginal probability of x times the marginal probability of y. Now, why did I need these? I needed those so I can substitute in for probability x and probability y. So this is less than or equal to, if I pick the upper bounds on the probability of x and y, that's these two, less than or equal to the sum over the typical set of 2 to the minus n h of x minus epsilon, 2 to the minus n h of y minus epsilon, like so.